So we see that if the process is completely known, then we can generate future data without waiting for the future. The problem is the process is not completely known. Because if you look at any statistical method, what does it really try to do? It tries to look through the data at the underlying process. We look at data only to understand the process that generates it. If we somehow know the process directly, then we do not need any statistics at all, right? If we know all the parameters, if we know the answers to all our test of hypothesis, why would you do estimation, test of hypothesis and all those things? So the very reason that it is a statistical exercise is because the process is not completely known. It may be partially known, but not completely known. So the technique that we saw just now, simulation, which is also called Monte Carlo technique, while it is a very useful thing, it does not solve our problem. So our problem remains. We have past data. Based on that, we have created some inference. We want to get some future data before the future actually arrives. We can do this if the process is completely known, but the process is not completely known. It is to solve this problem that a number of methods have been developed. These are all called resampling techniques, which basically try to reuse the past data, not directly but by some little clever manipulation to serve as a proxy for future data. We have seen that directly using the past data as a proxy for the future data is a very bad thing. It encourages overfitting. But we want to do the same thing but with a clever modification. There are a number of such clever modifications that are known. All these things are collectively known as resampling techniques. And we are going to take a look at some of them in these lectures. Now, any resampling technique must depend on partial information about the process that underlies our data generation. Some information, as I said, almost always we have some information about the process, and depending on what information we are assuming about the process, we may use different types of resampling techniques. All the methods that we shall discuss in this lecture will crucially depend on the assumption that the process is IID. That is, our data consists of IID observation, independent and identically distributed observations. That is a somewhat debilitating assumption because this rules out time series, this rules out analysis of variance. It is possible to relax this assumption to some extent to perform resampling even for linear models that we shall take up in the next lecture, and also for time series, which we shall not go into in these lectures, but the primary focus will be on situations where you have this IID assumption. So your data consists of some IID observations and your future data is again going to be IID from the same underlying distribution. I am not making any assumption like the distribution is continuous, etc., but IIDness is of great importance. The first technique for resampling is based on a very simple idea that takes mileage out of our ability to generate pseudo-random numbers using a computer. We saw that this was our situation. We had past data and future data both coming from the same underlying process. The trouble was that this process is only partially known. Something like you know the form of the process, but you know the values of the parameter. You know that the IID data come from some normal mu sigma square, but mu and sigma square are unknown. If only you knew mu and sigma square, you could use your familiar idea of simulation. Then what do? What does your gut feeling as a statistician advise you to do? Simple. You just estimate that mu and sigma square. You simply estimate mu and sigma square or whatever unknown thing there is of the process. Now you get an estimated process that way, so it is not the same as the underlying process. Even if you generate something from normal 0, 1, after you estimate, your mu hat need not be exactly 0, 0.01, 001, sigma square will be close to 1 and something like that, but should be pretty close. Then, what you do is, you apply your simulation technique from that estimated process. So you generate your future data not from the unknown true process, but from the known estimated process. Now, if the estimation process is pretty good, the estimated process and the true process are pretty close, in that case, you will hardly be able to tell that your future data actually comes from a slightly wrong distribution. It will serve your purpose quite well. So this technique is basically two things riveted together. Both the things are very commonly used in statistics. One is, if you do not know something, estimate it. The other thing is, if you know a process completely, you can use a computer to simulate data from it. Put the two things together, estimate followed by simulation. This is called bootstrapping, and that is by all means the most popular resampling technique known to a statistician. It is called bootstrapping. Now, depending on what information you have about your underlying process, your estimation process will be different. For example, I can give you this situation where, for example, your estimation process is a parametric process. Say you know that your underlying thing, as I said, is just a normal mu sigma square. You do not know mu and sigma square. Well, then you just estimate mu and estimate sigma square, plug them in place of the true thing, so you get a normal distribution, simulate from that. If you do that, that is called parametric bootstrapping, which is not the most popular way of applying bootstrapping. We shall see the most popular way of bootstrapping in a second, but first let's warm up with an example of parametric bootstrapping. So here in this example, I am starting with normal data. So I am playing God. So I have created, so I am the true process for the time being. I am creating my raw data from normal 0, 1, if I do not specify mean and standard deviation, R assumes 0 and 1 for them, and my sample is of size 100. So I generate it, so I get my data. That is the past data that I created. Now, I cease to be God. I start to play the role of a statistician. I do not know mean and standard deviation. So now I have to estimate them. I will estimate in the usual way. Mu hat is mean of my raw data, and sigma hat is standard deviation of my raw data. So I estimated mu and sigma. Now I will first create my estimated process, that is the estimated distribution. So I will just show it like this. So I will quickly run this mu hat and sigma hat. Let's take a look at how close they are. Mu hat is 0.04. So ideally it should have been 0. It is 0.04, and let's see how sigma hat behaves. That is 0.9, should have been 1. Okay, estimated process did not be exactly equal to the underlying process. A statistician is, after all, not God himself. Let's compare them by overlaying one density on top of the other. So I will take my estimated process, which is normal mu hat standard deviation is sigma hat, and I am going to plot not the density but the distribution function, the CDF, cumulative distribution function. Hence I put this prefix P before norm. P norm is the cumulative distribution function for the normal distribution, and I want to plot it between -3 to 3. I know it is not going to be interesting outside that. I use the color red, so let's see how it looks like. And this is my familiar normal CDF, where I am using the estimated mean and standard deviation. This is what I get as a statistician. Now let's see what got actually used for me. I again use similar thing car, but this time I use P norm without specifying mean or standard deviation, which means standard normal. -3 to 3, I use add equal to true, so I overlay on the last plot, and color I am using blue. So let's see how I get it. Yes, I am decently close to what God had created. The statistician has got his estimated process pretty close to the actual process. So if you are going to simulate from the red distribution, it will be difficult to tell it apart from true future data which will come from the blue distribution. So let's do our simulation. I will call it resample data. I am generating R norm. I will generate 100 more samples, but from our estimated distribution. So here I am using the prefix R, meaning I am generating random number. R norm 100 mean mu hat, standard deviation is sigma hat. Just a point to note here, I am using the same 100 here as well as there. So if my original sample size is 100, I am trying to mimic that process. So I am again using 100. So this 100 is known to me, so no need to change that 100. So I am creating my sample data. Let's create them. And to compare, I will make my histogram. So I will create my histogram of my fake data, my sample data, which looks like this. It might look like a little lopsided, but that is owing to the fact that I am making only 100 observations. In fact, if I do it once again, you will see that this lopsidedness has every reason to go away. Let me just try it out. You see, it is now not that lopsided thing anymore. And on top of it, I want to overlay the density of the true thing just to see whether this fake thing looks as if it comes from the real thing. So I will do this, and I will get a fit which is not very bad. And if I increase my sample size, you will see it will look even better. I will quickly run through the entire thing, making this 1000 and this 1000, and run the entire stuff very quickly. So I will get this thing, and you see the fit is pretty good. No one will be able to say that the histogram is not coming from that density that I have shown. It is coming from only an approximate version of the density. So what I have done here is parametric bootstrap. I estimated the distribution and then generated data from the estimated distribution.